Hi everyone, welcome back to Physics 218. So this video is for recitation on Thursday, May 7th. So I'm just going to use this recitation to introduce some new content so that we can take our final class on Monday as a synchronous session where we can maybe all say hi to each other and talk about any questions you might have before the final exam. So to recap, last time we talked about spin and some of its applications. Today we're going to shift gears to our final topic of the course, a very brief introduction to the physics of nuclei. So today I just want to introduce some terminology. I want to briefly talk about nuclear interactions and stability, and then I do want to talk about binding energy calculations since they draw on some material we talked about earlier in the semester. Atomic nuclei, as you may know from chemistry, are made up of protons and neutrons. Let's just remind ourselves of that. Now, the important thing you should remember is that protons have a positive charge, so they have a charge plus E, whereas neutrons, as suggested by the name, they're electrically neutral. There's a rich and interesting history about the discovery of the nucleus, in particular through the scattering experiments on gold atoms carried out by Rutherford and co-workers. Some of that history is in Night, if you want to go look at that. A few words of terminology and notation. We often use the symbol Z for the number of protons in a nucleus. And this is something called the atomic number. We will also people use a symbol N from time to time for the number of neutrons. Finally, the more common one you see is A, right? So that is going to be the total number of nucleons. So nucleons, the constituents of a nucleus, are the protons plus the neutrons. So total number of nucleons, which is going to be Z plus big N. Oops, that's a plus sign, plus N. Okay. Where you see this notation is in writing out what the symbols for various nuclei. So, to take an example, one typically writes for a given nucleus, one might write something like A and then X here, where X is the chemical symbol. That is the symbol one would see if you looked up a periodic table of the elements. So one will either write this, or sometimes one writes X, A to Z, although this is somewhat redundant, right? Because the atomic number, the number of protons, determines what the atom is. And so if you know A and the chemical symbol, or what atom it is, you can always infer what Z is. So as an example, for the most common isotope of carbon, which is carbon 12, we might write that with as C, so the symbol for carbon, 12, 12 protons and neutrons together, or in the convention here, we might write C12 6, even though the 6 is a little bit redundant. You should know that, right? If I know A and I know Z, I can always subtract them to find the number of neutrons. Something I wanted to mention about length scales is the size of nuclei. You can show via scattering experiments that the radius of a typical nucleus goes like the following. So the radius r of the nucleus scales roughly, so this is an approximate sign. This is an empirical relationship, not one that's like derived from fundamental physical principles. It goes like a constant r naught times a, the total number of nucleons to the 1/3, or the cube root of a, where r naught is approximately 1.2 times 10 to the minus 15 meters, or we might write that as 1.2 femtometers. And so thinking about what sort of certainly for small nuclei, right? R naught is basically going to set the length scale for the nucleus. R here is radius of nucleus. And then there's the total, this is the mass number, okay, which I should have written on the last screen. That's we call A the mass number. So a few things to take away from this that we're not going to have time to explore it in detail. So to reasonable approximation, so we can model nuclei as spherical. There's something called a liquid drop model for nuclei, and just as isolated small drops of a liquid are spherical due to their surface tension, we can think of nuclei as being roughly spherical as well. There's something interesting about this scaling, right? Because the volume of a nucleus, right? So the volume is going to be proportional to r cubed, right? And if we plug this in, right, since this goes like a to the 1/3, the volume of a nucleus is going to go like a, the total number of protons and neutrons. So what this tells us is that, right, the individual protons and neutrons act like small incompressible particles. And close-packed particles. So, just like you would expect if you were, say, stuffing baseballs into a crate, right? You would expect that the volume occupied would be proportional to the number of baseballs you're sticking in there. Nuclei, it turns out, behave in roughly the same way. And now for a quick word about the interactions between nucleons. When you have particles in the nucleus, things you need to think about include the electromagnetic interaction, and particularly the electrostatic interaction. I'll just call this whole thing electromagnetic, right? The key thing is that, right, so protons, right, because they're positively charged, there's a Coulomb force repulsion between them. So it becomes a challenge to explain in nuclei that have multiple protons what's keeping those protons together and what's overcoming the electrostatic repulsion that wants to push protons apart. Well, the answer turns out to be something we call the strong nuclear interaction. Or just the strong interaction or strong force. Now, what this interaction does is that it binds protons and protons. So I'll abbreviate protons as P, the way particle physicists often do. So you have PP binding, protons and neutrons, and neutron-neutron binding with roughly the same force. And it is this strong interaction that keeps my protons from just electrostatically repelling each other. A few other things. So the strong interaction is not electric in nature, in the sense that it doesn't affect electrons, and it's also very short-ranged. So its range is on that femtometer length scale as well, like what we talked about. So this is on the order of about 2 femtometers. There's one other nuclear interaction that we'll maybe say more about next time, namely the weak nuclear interaction. Right? Because the reason we need to consider the weak interaction is the following. If you assume that, well, the strong force is just going to always bind together protons and neutrons, well, what's stopping you from just sort of piling on additional neutrons? So, like, why couldn't I have a carbon nucleus with 20 neutrons? Or why couldn't that exist in nature? You probably know that doesn't. And it turns out that the weak interaction is strongly involved, strongly is not the right adjective, is involved in determining nuclear stability and nuclear decay processes. So we'll say more about those processes next time. But what I'll say now, so affects stability and decays. So what's sort of interesting about the weak interaction is that it's typically involved in it can be involved in changing the composition of changing what your particles are. So it can change protons into neutrons and vice versa. And so the other thing that it's like the strong interaction, it's very short range, even shorter range, in fact. And the sort of signature thing that you always have when you have weak interactions is it almost always involves neutrinos. Neutrinos are are particles that are electrically neutral, and so the question of they have either no mass or a very small mass. The question of neutrino masses and neutrino physics has been there have been actually a lot of developments in that within the last 10 years or so. Well, maybe I'll say something about neutrinos when we talk about decay processes next time. Next, I want to talk briefly about the subject of the stability of nuclei against decays. For that, I'm going to go to my laptop to show you a slide. A word about this graph. It's called a nuclear stability curve. So let me explain what we're looking at here. So nuclear isotopes, right, are nuclei that have the same number of protons and hence the same atomic number, but different numbers of neutrons. So every dot here represents a different nuclear isotope that's known to exist. The blue dots are stable isotopes, so those nuclei don't undergo decays, they stay around for a long time. Whereas the red dots represent unstable isotopes, so nuclei that do undergo decay processes we'll talk about next time. What we're plotting on the horizontal axis is the proton number, Z, and on the vertical axis, the neutron number, N. There are a few things to point out. So for small nuclei, so down here, right, roughly speaking, sort of this sort of line of stability that you sort of draw through this sort of band of stable nuclei runs roughly along the line where N equals Z. In other words, for stable nuclei, for small nuclei, they're stable when the number of neutrons is equal to the number of protons. Now, as you increase the atomic number here, right, you get that to be stable, you actually need to have more neutrons than you have protons. And then you'll notice as well that there are sort of unstable nuclei sort of on either side of this sort of region of stability here. Finally, the last thing to notice is that once you go above bismuth with Z equals 83, right, all other larger nuclei are unstable. So there seems to be some maximum stable nucleus. Now, a theory of why this is needs to explain sort of these behaviors. It needs to explain why N is about equal to Z for stable nuclei down on this end. It also needs to explain why N is larger than Z up here. Unfortunately, we won't have time to go into much of a discussion of the physics that underlies nuclear stability, although it does involve some of the quantum mechanics we talked about earlier. This is discussed in Night if you're interested in looking into it. And now a few words about the binding energy of nuclei. So you'll recall when we talked about relativity that we looked at the total relativistic energy of particles, and that for a particle at rest, the following holds. Of mass m at rest. Right, you'll learn that the energy is in SR units. We just said it was E equals m. In SI units, which we'll use now, there's a factor of c squared. And so one of the most important applications of this idea is in nuclei. So let's consider a system where the following holds, and I lost my blue marker, I'll be right back. back. So if I have a system of nuclei, so I'll just sort of draw this as a blob of dots like this. And so I'll just imagine this sort of imaginary boundary around my nucleus. Right? It turns out to be true for nuclei that the mass of the nucleus, so I'll abbreviate that m sub nuc, turns out to be less than the sum of the mass of the parts. And this is something I think we saw in a bunch of examples back in Unit R, where we had sort of processes where some things collided, for instance, and the final mass was not always equal to the sum of the masses of the initial things. So it turns out that for stable nuclei, right, in general, one needs to put in energy. And what's called the binding energy. And the symbol we use for binding energy is B to completely separate the parts. And this marker looks like it might be on its last legs. And so specifically, right, the binding energy B is defined as a mass you have to add to the nuclear mass to make this inequality. So specifically, right, m nuc plus our binding energy is defined to be equal to the sum of the masses of our parts. So now it turns out we can do some calculations with this, or let me actually solve for my binding energy specifically. It's going to be the sum of the mass of the parts. I lost a factor of c squared, forgetting I'm in SI units. Let's make this all consistent. M nuc c squared plus binding energy. There we go. Okay, so now, my bad, now we're good with something that is dimensionally correct in SI. C is so solving for the binding energy, right? Right, we then get, right, B equals, right, the sum of the masses of my parts, sigma m parts, minus my nuclear mass times c squared. Sometimes we call this thing the mass difference, delta m. So if I highlight this, see if this marker is better. So our binding energy is delta, so we can call that delta m, and then our binding energy is our mass difference times c squared. Now, oftentimes our nuclear masses, and I'm going to include a slide showing you the masses of protons and neutrons and electrons, right? They're typically given in what are called unified mass units. Use unified mass units. And what you really need to know is the following. So 1 U turns out to be 1.66 0 9 times 10 to the minus 27 kilograms. And I've kept a bunch of digits here because generally in nuclear calculations we're talking about fairly small differences in mass, so we do need to keep, you shouldn't just round to like 2 or 3 sig figs like we normally might in physics. But the 5 sig figs, the more useful one is actually to work in electron volts, and that turns out to be 931 4.48 mega electron volts over c squared. So I'll go and erase the board, and then I'll walk you through one calculation of the binding energy, and then I'll have you try one as a whiteboard exercise to wrap up today. So let's consider trying to find the binding energy for helium-4. It's given that helium-4 has an atomic mass of just over 4 unified mass units, so that's something you could look up in a table or on a periodic table. So our strategy to find the binding energy is to find that mass deficit, and then we'll be able to use the binding energy being equal to delta m c squared. Okay, so let's start by finding the mass deficit, right, which is the difference between the sum of the mass of my parts minus the mass of my nucleus. So here we have to be a little bit careful, right? So we have so the nucleus of helium, right, has helium-4, so it's got 2 protons and 2 neutrons. So I'll write this as 2m proton plus 2m neutron. Right? And then we have to subtract the nuclear mass. So this, we have to be careful because the nuclear mass, right, it's the atomic mass of helium, but that atomic mass also includes the helium atom's electrons, right? Helium has got 2 electrons, so we need to subtract off the mass of 2 electrons to get just the nuclear mass, right? So includes the electrons, subtract the electron mass to get the mass of just my nucleus. And so that's the one tricky thing about these calculations, but the rest is not so bad. We just have to plug in values from like the table that was in the slides. And if we do that, let's work that out. So I get, so 2 times 1.0028u. Again, we should keep something like 5 or 6 sig figs here, plus 2 of my neutron mass, 1.00866 u. Then I subtract off my helium nuclear atomic mass by that, which is minus 4.0026 units for the mass of my helium atom. And then I have a minus, so that's a plus, actually. So that's plus 2 times the mass of an electron, which is 0.00055 unified mass units. Plug and chug on this, and then I get delta 0.03038 units. unified mass units. And then I can just find my binding energy in MeV. My B is my delta M C squared. So the easiest way is to just put in U in MeV per C squared, so that's 0.03038 U, right? But we know that one U is 931.48 MeV over C squared. So that's my delta M, but when I multiply by C squared at the end here, that just cancels here in the unit. And so what we end up with, I just multiply these two numbers, and I get 28.299 mega electron volts. So now let's have you try this for an iron nucleus. I'll put the solution in the class slides. And then we'll continue our discussion of what's called the curve of binding energy and what that says about what does and doesn't happen with stable nuclei when we come back on Friday.